Hello there, and welcome to my new series and welcome in the English section of my channel. Today we are starting a new project. The project is called CompuTec, where we will build one after one PC parts or like computer parts in Minecraft. Today we will start with kind of a tape drive with the plan of achieving lots of storage, addressable storage, in kind of a read-only memory fashion that you can use for BIOS or hard programming your programs into your Redstone computer. And we are planning to do a few RAM or flash storages in the futures when I've come up with a few space efficient or more space efficient designs that are easy to pull off, easy to steer, and support a high bandwidth of memory so that even a slow clocked Redstone computer can benefit from higher speeds of the storage and doesn't get bottlenecked from the storage. After all, I will try to enable the world download in the description below, so feel free to download the world and use the stuff in your own fashion. Just if you do it in a commercial way or try to design your own computer, make sure to put my name somewhere where people can see it. That's all I want from you. After all, I will try to keep the CompuTec modules efficient so they don't produce much lag, but I can't promise that it will be always lag free. Today we will start with, as I already said, a tape drive, and we will build it part by part. I will kind of cut it, and the tape drive will have a steering segment that makes it search for the address you insert. So the computer requests an address, a memory address, and it will continue until it found the memory address and then output the value with the output signal. So what we're gonna need is 1, 2, 3, 4, 5, 6, 7, 8 bits for an input bus. Then we need, since this is a ROM cartridge kind of, we don't need read and write. That is unnecessary, so we will make this black. And we will 1, 2, 3, 4, 5, 6, 7, 8 need a 8-bit output signal. And we need one more signal. That is the basic communication signal, and we will need the read signal. So we don't need the write signal, we only need input bus, read, output bus, and general communication signal for, yep, that is actually the value you requested, dear PC, dear CPU. So this is the port that will be activated. I will locate it here when we found the address. So we have an 18-bit bus. This is kind of a low memory bandwidth, and you can, without any problems, increase it by 8 and 8 bits, so you always get a full byte. But since most of the Redstone computers aren't that powerful at the moment, I won't add a 16-bit interface, like 16-bit read interface. But I will include one on our build SSD. So this is kind of our input. We're gonna build the storage behind here, and we will cut so I can enable or like build the basic bus. Okay, what we basically now have done, or what I basically now have done, is I elevated the complete bus and utilized a function that the repeaters have that most of the people sadly are tending to forget because they can't find an obvious use case for it. Because you can actually lock repeaters in place that they keep the signal that they received while they were not powered from the side. And since our ROM drive actually needs some time to figure out what address, or like where the address is on the tapes, like we will build one tape, but you easily can extend the bus with a lot of stuff. Like if you want to add a whole another tape, you just have to add another address bus, like this, for example. Like for more bits will mean a second tape, 4 more tapes, 8 more tapes, 16 tapes, like you can have 31 tapes with this 4 address buses. So you can actually store quite a lot of ROM data in here. So the only thing you need to add is like the connection circuit. If you do this, you will have to physically break the connections to the driver circuits of the ROM drives. And for example, if you wanna you have 2 tapes, like you have a single address bit, like, or a single routing bit for a second tape. That means if it is low, you have this physically connected to this to the driver of the first tape. If it is high, you have this physically connected to the driver of the second tape. So you can add quite a lot of storage with just adding 1 more bit or 2 more bits, or like whatever, 10 more bits, how big you want to have it, like how, depending on how big your program is and stuff. But for a basic BIOS, it should be enough to have like 1 large tape drive, because you can build the piston feed tapes that we will use for a tape drive. You can build them apparently pretty large if you just not only use this kind of setup, but if you use like this, this kind of setup, and kind of just move it down and feed it in here afterwards, like apparently you can have a pretty large tape that way and add it back to the beginning. I don't know where the beginning is. Oh wait, the beginning was there. Wait. Like having this pattern enables far more storage, if as if you can see, than normal quad piston feed tape. And on this way you can have a lot of more storage. And to utilize the full 8 address bits, you're definitely gonna need this setup, because you can't build a tape drive physically that large with or 4 piston feed tape physically that large to utilize all 8 of the data address buses. So like all 8 bits of it. So you kinda have to use this snake pattern for the drive. But it's up to you if you use my setup. We're just gonna build a simple setup with, I don't know, 20 or 30 bits that we're gonna utilize. Or 30 bytes of storage that we're gonna utilize. It's kind of more like a proof of concept here. We're not actually gonna build giant machines, because that would definitely overextend the kind of space that this video has, or what it is intended for. This is just more a proof of concept video, or proof of concept video format. We're not gonna build a PC, we're gonna build single parts and maybe set a few standards for future Redstone PCs that will be built. Kind of like a form factor, and kind of develop a motherboard for make it easier for people to develop PC parts for Redstone PCs. Depending how much or how far of a range I will get with these videos. And kind of our next goal is to utilize this. Like, wait, misclicked here. If I activate this address bit and then activate the save, even though this signal ends, it will continue to spit out the high signal as long as this save is on. So what we're gonna do is build a NOR latch that keeps that bit high, like the save bit high, until the tape drive replies, "Yup, I have found the value of the address and outputted it to through the address bus, through the output bus, and have told the PC that I am outputting through the address bus." So at the moment that this bit will light up, it will also activate the NOR latch to deactivate the save. On this way we're gonna avoid losing the address on the way of searching, because our driver board will need a constant address signal, and since most of the builders or creators don't keep this in mind, I think we will solve this problem ourselves on our own driver board. We could just lead the address bits to the driver board and do it completely on the board, but I kinda like to do it here because apparently it's easier to solve problems at the beginning instead of forgetting them later on. So we solve the main problem of keeping the signal up directly at the input bus, and directly utilize these 2 bits to save the address and delete it again. And that, oh, by the way, that is one of the ways we're gonna build our RAM later, because that is kind of a really good DRAM setup. It's small, it's good to utilize, and apparently it is not the smallest. You can build smaller, but this is kind of one of the fastest DRAMs you can do. Like, building caches out of this stuff is this is basically the fastest way to store and delete data in Minecraft. The only problem it has is it's volatile, so it will lose its data if there is an issue with the save line. Don't use it for permanent non-volatile storage because it is not non-volatile. This is more like a cache setup that you use in your CPU or in your DRAM cache, or in your DRAM modules of your PC, because it is fast, it has a low latency, but it is volatile. It's nothing to store permanent data on. And what we next gonna do is hook up the cache circuit kind of, and continue getting the bits to the driver board, and we gonna we're gonna put these bits physically closer together, compress it, thanks. We're gonna compress the bits physically, to get kind of this setup, because this is what our driver bot later utilizes. So we kind of get this setup, one line or one bit, and use the signal range of redstone to physically only connect this with this, because it only can power this, because this would be 16 blocks, this is 15 blocks. So we kind of utilize old game mechanics that redstone has in this build to make it work, because having a bigger address bus, not compromising this, not compressing this will make your drive significantly larger. This kind of output bus will be compressed too, so yeah, if you are trying to build larger tape drives with 4 or 6 drives, 4 or 6 tapes, you will benefit from compressing the input bus. Because on this one tape, it might only be 8 more blocks. But if you have it on 4, it is already much larger. So keep it in mind, we're gonna compress this, and we're gonna spread it up again. So we need 2 more boards to do this. We will be back after I hook this up and build the compressing circuit. Kind of, it's not a circuit, it's just literally a compressor. We push it to maximum signal range and then punch it out there. Okay, so what I now have done is basically what I've said. I hooked everything up, and every lock that you see here is where I had to interrupt a connection. Like this was connecting, because this is the address bit from below and this is the safe bit. They can't connect, so I placed this lock to visualize for you where you have to watch out if you compress it as far as I do. So the basic concept of this at a moment is, let's deactivate the safe bit, or the read bit, not safe bit, don't call it safe bit, it's the read bit. We have spread this redstone as across 15 blocks. So what this is like, if I do now activate this, you can see this bus, like this bit is flashing. This one routed here. And only this repeater is flashing because this is 15, and with it spreading out 15 signal strength of 15 flux, I think is the measurement. I don't know. Like, it is like you could only do 15 steps. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. I kind of jumped one of it. But the concept is like, you can only cross 15 of this. But this is number 15. But if you, like, go to the side one step, this is number 15. You physically can't reach that one. And it also works if I activate these and this on the same time. Like, with this setup, you don't have any limits of bandwidth. You can make it physically as large as you want to. And since one key is, or one bit is addressed to literally one bit, you can activate all at once and they will all flash up, or activate only a few of them, and only a few of them will lit up like that one that you activated. Just make sure that you measure correctly and have this, from this redstone to this redstone, be 15 blocks. Otherwise, it will interconnect with the other repeaters, and then you will get a crossfire, like activating this one and having literally activated this, and this bit, and you don't want to have it. How I compress this should basically be self-explaining, I think here. Like, I routed them together, and to prevent interconnection, I laid blocks above it. Yeah. This is the result, and what now happens with our address bus. There will be a lot of stuff happening. We're gonna lead one through to the address bits. In the address bits, there will be a, like, or to the main control circuit. The same thing will be in the tape. And basically, this is a very stupid, very stupid tape. So it is good for sequential reads, like reading 1, then 2, then 3, then 4, then 5, then 6, then 7, and so on and so forth. But reading number 64 and afterwards want to read number 1 will mean you have to go through the whole tape and afterwards read out the 1. So if this, what we will implement is, or what we might implement, I don't know yet, depending on how large I will build this, because when you build more tapes in, you have to lay this physically further away, and then you have more space to use. I don't know if it fits here without getting enormous. An automatic that starts spinning the tape back to address 1. So basically, if it read it out and isn't in use for a minute or so, it will start to spin to get back to address 1. But this will take up a large amount of space, and we don't want to use a large amount of space. And since the intended way for this is to be a kind of a bias, or yeah, kind of that, it is lots of sequential reads anyways, so yeah. And guys, it is a tape drive. I don't know what you expected. This is not an SSD. someone far smarter than me could implement a logic that looks if the address is bigger or smaller than the last address, or like the address it has at the moment, and then spin it in this direction, but yeah, that is something that has to be done by a person that is far smarter than me. So yeah, what we actually gonna do is like literally let it spin until it finds its address, and then take the address and send it to the output bus. This is a basic storage, nothing SSD-like. The SSD-like performance we're gonna get with the flash storage we're gonna create at some point. Like the non-volatile flash storage kind of type. So, yeah, when I'm finished with development, at the moment my concept is not working, but that is not the point at the moment. Yep. And what is gonna happen is we're gonna do a kind of mechanic that will spin the tape drive bar 1. When it detected a spin, it will test if the address is correct. If it is correct, it will give out a signal to the output bus throughout the tape. Like it will go through the tape, power the output sequence, power this bit, reset this bit, and give it an output. What we actually will implement is a signal buffer. So this signal is longer than just the single tick signal that we are receiving from the tape, because it will be a single tick or like dual tick signal, and we will expand it to a 15 or 16 tick signal, so it is long enough for the slowest Redstone computer that is actually working, and not just a fake ROM drive with kind of stuff, yeah. Like the actual working PC to pick it up and work with it. So, yeah. I repeat myself again, this is not an SSD-like performance. It is just a basic storage. If you want to run a program, a large program, you have to store it somewhere, and you want to do a lot of sequential reads, you're fine. If you don't want to do a lot of sequential reads and just want to have an SSD like performance, you're fucked. That is basically it. Okay. So what we're now gonna do is, yeah, we will implement the knowledge here, and afterwards we will physically have it implemented here. And we will start to build the logic, the driver logic or the detection logic for the address. And I will hit you up, I will continue filming when I'm done with this. So, yeah. And we will see for you in a second. So, what I now have done, I basically built the circuit for detection if the address given from the address part of the tape drive matches the address spit in from the request, from the IO, and basically what now happens is when this and this address are different, like this and this bit is different, bit 1 here is different from bit 1 here, means this sensor output here, like this is the sensor output. Every brown strip is a sensor output, will emit a redstone signal and push it through the sensor bus, kind of. This is a bus officially. So yeah, and I'll put it here, where a redstone signal will close the circuit for the spinning circuit, but will close the spinning circuit to work. Therefore, the tape will spin, and will spin until everything is off, like both addresses are the same. Then this output will break the turning circuit and activate the output. So the output power thingies are powered, and the output is pushed through to the bus, to the output bus, to the waiting computer or waiting CPU. The output bit will go high, and the output value will be outputted, and the latch will be resetted. What I've basically done is doing a bit internal timing. We extended the pulse of the input, so the pulse is for sure in the register cells, in this gray register here, is for sure in the register when the register saves the address, because the address has to be in there for the register to save it. So yeah. And we have extended pulse length of the read a bit. So the latch that gets activated here, like this latch, doesn't turn into a clock, because this is apparently a problem. So I've extended the pulse length, the minimal pulse length, so long that one of this gets turned off, the repeater gets turned off, and then the pulse stops. So there's no way of clocking. Because when there is a clock, even though the clock burns out after, I think, 6 pulses, every pulse will lead to deleting the address that is saved in the address register here. And since we don't want our register cleared yet, we prevent this from happening. A register will get cleared when the violet output bit, like the output bit, is going high. Then it will reset the latch to 0, so the register opens and every stored value is deleted, and the general signal strength on the bus, like on the address bus, is 0. Because the 0 address is always leading to the closing of the circuit. That means our tape drive doesn't go in a dead space, because we don't have a 0 address, like address null, in the tape. So therefore a complete 0 address will always lead to the address be false, and therefore always the circuit closed, what means when a new address is inserted and it does not match, and for whatever reason our bit happens, read bit happens to be faster than the address bus, then the tape drive doesn't get stuck. Like, if for whatever reason somebody, by implementing this in his build, messes up a bit, like, I don't know, one of the delays that will follow here, messes us up, and the address bit, the read bit happens to be faster than the address bus, then this will prevent the drive from getting stuck. Because if there would be an address null, and the tape drive would be on address null, then this being on address null and this being on address null would lead to a invalid state of the tape drive, because even though the circuit is closed, or should be closed, it is opened. Because this shows null, this shows null, it is opened. The pulse from the read bit will run out and the tape drive wouldn't get started. So we don't have an address null, but here's an address null as a default state. So we can't get stuck because it's always false and it will always close the circuit. Like idiot safe. That's actually the reason why we will implement a pulse shortener here. So we will only get a single starting pulse and therefore not clock our system, because if this is complete through, like if this stays high for too long, it won't turn this anymore. Like, everything will be powered, the tape drive is broken, and everything is shitty. That is why we need a 1 tick length of pulse. And that is what we are creating up here, or what we will be creating up here with a pulse shortener. That our tape drive doesn't get broken in normal use. Like, it doesn't spin per default, and it will only spin if we input that it should spin. And if we input once, it should spin. The signal will travel through the turning circuit and will come out again. And then is where the test happens if the addresses is the same. If the addresses is not the same, the circuit is closed and it can continue running for another time until the address is the same, every bit is the same. That means the circuit will be broken, the signal will run out, and on the same time, by this circuit being broken, it is detected for the output bus, like the readout pins in the tape drive will get powered and will output their value to the output bus. The value will get buffered, so it can be a longer pulse, and we have a longer tolerance of output values, like, or of clock timings. If the clock is too slow and the signal runs out before the clock is ticking, this is a problem. So either way, if this signal is too short for your computer, if you're downloading this build, then you should implement a memory controller or a buffer. We will buffer this signal with this output thingies, like with this repeater, the output buffers, or we use it as output buffers. It will extend the 1 tick signal to a 4 tick signal. If this 4 tick signal, for whatever reason, happens to be too fast for your computer, buffer it. Since we don't have a mainboard released yet, this means you have to buffer it yourself when you build your computer. We will release a mainboard at some point where we have the standard interfaces, this 18-bit interfaces for tape drives, and we have a few other interfaces. And a socketed CPU. This will be very interesting because we will maybe set a new standard for motherboards and stuff in Redstone computers. I'm pretty excited. I hope this video gets enough attention to actually kick it off. Well then, we will continue. I will film the next clip when I have routed it up here, added a pulse shortener, added the circuit breaker, and yeah, when I've done this, I will hit you up again. Okay. I've now hooked up this section here. And installed the address bus on the other side. Here will be the readout for the address. And the address as well as the single bits and programs need to be hard-coded on the tape. That's why it is suboptimal for anything dynamic, because you can't just change blocks real quick. That's just not how it works. Therefore, it is perfect for program memory. Like if you wanna install a program on your PC and you'll have to type it in bit for bit, then you can hard program it on here, and your PC can load it from the hard drive or from the tape drive whenever you need it. So this tape drive is kind of a ROM drive. Yeah. So I've installed the address bus, I've installed the reader, like the detection if it's if the address are matching with the signal transmission. It is done with a little, this can go away, so torch beneath that hard powers this block. That signal can be extracted here. We need this repeater that it doesn't interfere with this one. Then it gets leaded to here where it will be used for the readout of the value. So this will also be shortened when we are done. I think I will insert the shortener here and then just lead the single pulse through the whole segment. Like we have to route the cable back to here through the readout, and then it can run out, and then it will just flow in the eternity into the PC, or like into the CPU. Next clip we will have the tape drive, or yeah, we will at least have this little pulse shortener, and afterwards probably the tape drive, and then I will show you how we program the addresses here, but I think you will basically already know how we will do it. For everyone that is wondering why we have this big large yellow area, that is the rest of the circuit board that is left, and apparently a pretty good ad farm. Well, yeah, it is. We will have the compressing kind of circuit on the board to lead out to the addresses, because the address will, the value will come out compressed, and we need to do a breakout to the single pins for most computers to use it, because that is a far easier to work with interface than just having everything compressed together. Not only for in the drive itself, because I have lots of space to implement the registers, like the register cells, the memory cells from the register, okay, this way, but also for the PC creator to work with it. Like we will delete this real quick. This nobody needs the switches anymore. I've implemented them to show you how this stuff works, but we will have them later. But that's basically how the interface looks, like the I/O. This is what you will work with if you will use this tape drive. Every orange is the address bus, gray is read, to confirm that you want to save this. To confirm that you want to save this address that you are inputting in the register to have this work and get the tape drive started. The wallet is the output pin, like it confirms that the thing that the value is coming out at the moment for your clock to work with. You can basically, what you can do is build registers outside of it, so when this signal comes, you can use it to power your registers to save the value that's coming out. I will hit you up again when I'm done. And welcome back. What I've now done is I linked up the cable for the readout. Currently it's active because I actually have Torch installed there to test for the signal strength. That is the readout line, like that gets triggered whenever it shows true. Like it shows that two addresses are the same if they're matching, and every sensor is on low state. Then this block goes back, and this gives out a signal that powers this readout pins for a short while. Like, look, you might be able to see it. Yeah, there it was. You saw it, I hope. Let me do it again. Yeah, this little repeater's flashing. That are the readouts. That gets, because this is powered, pulse is shortened, pulse is leaded towards the readout. This is the address readout from this. We don't need much tech here because it's literally just this address has to be read out constantly anyway, so it doesn't matter if it's a high-tech stuff or just a torch with a repeater. What matters is the stuff goes through the block and has a set signal strength to not fail the bus. Because you see, both of the bits are high, and those two bits on the bus are high too, so it sets those two sensors to false because that two bits are not high. If I set them too high, what I can't do at the moment because I don't have levers. Yeah, trust me, if I would set them too high, like this bus too high, it would show off that these two are the same, and it would not show off because, yeah, apparently one is missing. But now it would show off that both of the addresses are the same and go low and detect this and activate the readout. Next thing we will do is implement a driver circuit and add all pistons. Here's one missing, and then continue the row all the way through to this and build the blank wheel. And then, yeah. At the moment there are 71 71 memory addresses because the complete null is not existing. Address null is invalid, that's why it isn't existing, so it's 71 and not 72. It is reaching from 1 0 0 0 0 0 0 0 to 001000100. That is the 72 in decimal, or yeah. What means 71? Because we don't have the complete 0. There's the output bus. There's the address bus, like address. That's I call it the same, so you can see it. What is bus? What is what? So you can understand it better when you're downloading this world. We will meet again when I have finished the piston feed tape here. And we're back. I completely wired up the pistons. Now I will connect them to the control circuit over here. That they and do a repeater line that they get powered at the right time. And what I also did, I implemented go away. These two. I implemented don't need this anymore. Like a little circuit, in addition to this, that can turn off this torch. Our problem was that the torch was turned on, which means when the address is already correct, because you're reading the same address twice and thrice, and yeah, then your read bus won't reset. So you can reset your read bus automatically. It gets reset every time. Because when we activate it now, the pulse shortener cuts off here. Yeah, stuff happens, that's good. Nobody needs it. Because our address is already correct. This is in a retracted position. What happens? This torch gets turned off, this gets turned on. So it goes through the circuit, through the output circuit, and to the output bus, to the output bit, and resets our latch and therefore our output bus. In reality, we have entered the correct memory address, like this is address number 3, because I had to go physically one block higher, because these pistons were butt powered by this redstone line when it was one down. We had to avoid it. So now it is address the third bit lit up. Is actual the correct address at the moment. And if we click the read, it goes through, the output bit goes on, don't know why I keep saying but, and resets our input bit. However, this only happens when the address is correct. If we now load an incorrect number in the address, or in the register, like, for example, 0, like the null number, it looks for that number, and since it is wrong, we see this doesn't match. The third bit is wrong, doesn't equal. Our sensor jumps on. It is in an extended position and jump started and enables the turning sequence. At this point it would turn forever, because null is the null position is something you can't use, but it's an illegal position. Wait, that's illegal. And it will never find the address, so yeah. But yeah, it would turn until it found the address. What I now will do is hook it up, attach the steering circuit, and lay the front bus or the output bus down to the I/O, the main I/O. What is, by the way, an I/O from the standard SHTD1, and it is not a complete. The complete I/O standard would look like this. To have one GPIO, like you can use it for whatever you want, but minor details. That is a complete SHTD1 standard for communication. It is every time starting with the inputs. This is bit 1, important. Not this bit 1, this is bit 1. This is bit 1, this is bit 8. And number 9 is the GPIO. In this case, it is kind of hooked up to an empty storage cell, so you technically could add another a bit per operation, but you also could add a turning indicator that this thing is turning. Yeah. As I said, minor details. We will remove this for now. But this is the SHTD1 standard. There's also the SHTD2 standard, which supports not 1, but up to 8 tape drives over 1 GPIO, or 1 main IO, and actually has the flipped bus, like this is mirrored, but SHTD2 is not mirrored. It is correct hooked up, and SHTD2 has a larger address bus and a larger output bus, because SHTD2 not only supports 8 but 16 bit output. And yeah, so basically SHTD2 has, I think, 3, yeah, it were 3 more bits. No, wait, it supports 15 tape drives, up to 15 tape drives, and up to, I don't know how many kilobytes. If I remember correct, 2 kilobytes, but let's settle for it's enough, because you will never need 2 kilobytes of storage on a Redstone computer. This already can store more than you will ever need in your Redstone computer, like this 8-bit bus, but we are only in the 6th bit right now, and there are 2 more bits to go we could use, so the capacity is pretty large on this one. Anyway, I will hook it up, and then we will see it running and searching for an address and outputting a value. I don't know, I will program something in here. Like this is the empty storage reel, like this is the address wheel, this is the storage wheel, this is the detector reel. This little bit, please don't forget it, it's important. It indicates that the reel has turned. This is an indicator. This red line, it is the indicator. It turns with the reels. They turn synchronous, kind of, and every time this turns, there is an address check set off. This is what actually sets off the address check. When this turned, it will check for the, it will test for the address. If it's correct, it will output this value. If this is not there, there will be no address check. Don't forget this if you are rebuilding it. This is very important. Okay. So we will see again in, for me, it's probably half an hour. For you, it's not even a second.